Solomon, how are you guys doing? All right, so you're all welcome. Good evening, everyone. You're all welcome. I think we can go right away into business. Okay, so you're all welcome. This is a brand new week, so welcoming you guys into this new week. And I just want to find out. Okay, I just want to find out how has the classes been? Okay, how have the classes been? Is there something you hope to achieve in the class that you have at least started achieving from the classes? Let me just take just 2 feedbacks and then we'll start the class for today. If you are anybody, if you have a comment, you can raise your hands. I just call on you. Yes, please, anyone? Okay, Mendy, you can go ahead.
Okay, yeah, good evening, guys. Happy New Week. It's been actually, insightful thus far, and I really look forward to. Having to, work practically and technically with these concepts. Okay, that we've actually learned up until now, and even the one we're going to be learning today, because actually to be a solid backend guy, you need to know data structures and algorithms. I really look forward to us having to build something individually and collectively. Okay, via this concept. So.
Okay, that's great. That's great. Thanks for that. Yes. Any other person? I'll take one more person and we'll get into business today. If any other person, you can raise your hand and I'll call on you. Okay, just one more person. All right, we're short on time and we have a lot to cover today, so let's get straight into business. All right, so today we'll be looking at the overview of algorithms and data structures. And when I say overview, what I mean is that there is more to it. So this isn't going to be like the class that sums up all the knowledge you need to gain. You need to also do your own personal study. However, I want to introduce you to this concept, and for those who are already familiar with this concept, let's look at it together, familiarize ourselves with it. So today we'll be looking at algorithms and data structures. Okay, so let's get busy. So once again, my name is Benjamin. I'm a MERN and .NET full stack developer, and I'm going to be bringing to you this class. This is the overview of data algorithm and data structures. And we're going to be looking at this content. So for today, we'll be looking at what is an algorithm, okay? Algorithm characteristics. We'll look at common algorithms. We'll look at the algorithm performance and what are data structures, common data structures, and we'll also be looking at practical applications. So this is going to be the overview of what we're going to do today. So I'm not alone on this. I have here my partner in this. This is Prosper. He's a mentor, and you can always reach him on the Slack channel. And he is a backend developer, experienced with NodeJS, MongoDB, Express, and TypeScript. So he's a go-to person for this course. So any challenge you have, you can reach either me or you can reach him. So let's get straight into business. Now, what is an algorithm? An algorithm is a precise step-by-step series of rules that leads to a product or to the solution to a problem. So it's a precise step-by-step series of rules. Now, an algorithm is more of your recipe. You can think of it as a recipe. A recipe has like the time things should come in, what should be done. And, last week we were considering object-oriented programming. And when we consider object-oriented programming, we looked at 2 concepts. One of them was the procedural, programming, which had to do by a step-by-step process. Your functions are basically executed in order of how they should occur. And then when looking at object-oriented programming, we look at it from a different perspective as you are describing the objects, okay, the objects there, the entities, their behavior, and how they interact with other objects. Now, that was another concept. Now, algorithm also here now is a concept, and you can look at it as a precise step-by-step series of solutions that lead to a product. Now, it is you putting together the steps of how you're going to solve it. So there is no one-size-fits-all algorithm. There's no specific algorithm that will work in every condition. So algorithm is basically related to the problem, and there can be different approaches to how the problem is solved. So in essence, an algorithm is, your own thought process of how you're going to solve the problem, and based on experience, some algorithms perform better than the other. So we want to understand what are the characteristics of algorithms. How do we, characterize them? So one of them we characterize them is called algorithm complexity. Now we have two general types of algorithm complexity, and one of them is the space complexity, which talks about how much memory does it require. Your computer is basically a machine with a finite amount of memory. It has an amount of memory space. And when applications are running, you have, for example, when you're talking about your RAM, okay, you have when you're working maybe with a 1 gig RAM phone, 1 gig RAM mobile phone, there's a limit to the amount of applications you can have running at a time. You begin to see some systems complaining of space, hanging and things like that. You also, aside that, you realize that some applications, use more memory than the other. So you want to ask yourself, okay, how much memory does it require? And now we're not talking as in terms of applications now per se, but we're talking about now like this algorithm or the process, what or how much memory is it going to use up? So every operation you want to do, you're considering how much memory is it going to use up. And then this lead to, considerations here and there. It's what's going to make the whole lump sum of whatever big application we're making. So algorithm, we look at space complexity. How much memory does this operation require? The next is time complexity. How much time does it take to complete? Okay, so you have a start and you have an end or a finish, okay? How much time does it take to complete this operation? So we'll look at that in details. Now, the next is it's categorized by inputs and outputs, okay? So you categorize by inputs and outputs. I think I should put inputs in plural. Okay, so it's categorized by inputs and outputs. Now, in terms of inputs, what does the algorithm accept? Okay, and output, what are the results? So when we're talking about what it accepts now, we're asking like what type of data, what amount of data, what kind of data. Okay, so how large is the data set? So these are some of the things that we look into when we're talking about inputs and outputs, and then how does it present the result? What kind of result do we get? So that's what we talk about by input and output. Then we have classifications based on serial and parallel. And when we're talking about serial and parallel, we're looking at, like it's a process. Is this something that is single-threaded? Is it an application that is running one at a time? Okay, or is it parallel? Is it like multiple concurrent things happening? Okay, so when we are looking at that is one classification. Okay, so you could have something that is moving at a time or something that is concurrent, multiple computations of things happening at the time. Then you have exact and approximate. Now, when we say exact and approximate, there are certain calculations or functions that will always give you an exact result. Okay, they will give you an exact result. And there are some that will give you an approximation. So an example, I think the best way of describing an approximate algorithm result is a facial scan, for instance. Now, the facial scan, you would not always get an exact match of anybody's face, even if it is the individual who took the picture from a different angle. That facial scan might not, have a perfect match. So generally, those kind of algorithms are more of approximate algorithms. But when you have a fixed or an exact result, then that is an exact algorithm. So you could have approximate algorithms, you could have exact algorithms. Even in petroleum engineering, back then when I was doing programming in petroleum engineering terms, we had certain kinds of simulations that were more of approximate, because you don't know the exact the exact contents under the surface. So you have more of an approximate result or algorithm. So that is the difference between exact and approximate. Then we have deterministic and non-deterministic. Now, deterministic is saying, okay, this algorithm or the result now we want to get, is it something that is always the same at every point in time? Okay, so it is deterministic. It has a fixed result at every point in time. If you provide, okay, yes. So if you provide a particular set of inputs, okay, if you provide a set of inputs, then you will have that the result will always be the same. That is deterministic. And when you have non-deterministic, your result will not always be the same. Okay, so it's non-deterministic. You're not getting the same result. So for example, if you're looking at an operation like math.random, okay, where you are having randomized like a guessing game, you will never have the same results. If you're having the same result, it's more of a probabilistic occurrence. Okay, so the chances are you will not get the same result. So it's not deterministic, it's more probabilistic. So that so these are ways that you could classify algorithms. So when we have the complexity, which involves space and time, and once you hear space, you'll be thinking of memory. Once you hear time, you're thinking of how long. Then you have the inputs and outputs. What does it accept? What does it return? And then you have classifications according to this. Now, there are certain algorithms that are common. Okay, there are certain algorithms that are common, and some of such algorithms that are common to be the search algorithm. Now, the search algorithm tries to find a specific data. Okay, it tries to find a specific data in a structure. So that's one algorithm. Okay, tries to find a specific data in a structure. So there are different ways you can go about it. So search algorithms, there are different types of search algorithms, which we should look in details in our class on Friday. We'll look into it in details. Okay, so search algorithms with practical examples of them. Then we have sorting algorithm. Now, in sorting algorithm, this is taking a set of data and it places them, okay, it places them in a particular order. So it takes a set of data and places them. I don't know what's happening to my spelling today. Okay, so it takes a set of data and places it in a particular order. So that is a sorting algorithm. So the order could be maybe according to the time. Okay, the time, it could be sorted by maybe alphabetical order. So there are different ways that it could be sorted depending on your own choice. Then we have computational algorithm. Now, this takes a set of data and derives another set of data from it. Okay, so computational algorithm looks to take a set of data and it derives another set of data from it. So that's computational algorithms. And we have a lot of them, okay? We have a lot of them. Some of them are functions that we use on a regular, but we have not quite taken time to think about, those data, okay? Then we have also the collection algorithm. So the collection algorithm works with collections of data. So here we have more of a simplistic algorithm here. Okay, so this is the Euclid's algorithm, and to find the greatest common denominator of two integers. Okay, so it says find the greatest common denominators of two integers, and how this is done is that the largest integer that divides two numbers, okay, without leaving a remainder, is what will be referred to as the greatest common denominator. So for example, you have maybe like two numbers, 20 and 8. Now, you want to look at what is the largest factor, okay? What is the largest factor? So for 20, you have, 1, 2, 4, 5, 10, and 20 as factors. And for 8, you have 1, 2, 4, and 8. So then when you look at them, you see that the largest you have is going to be 4 on both sides. But here now, this is you thinking about it and writing out your own solution now. But what if you were to tell the computer to do this using this algorithm? So there's a way to go about it. So what I'm going to do here is I'm going to share, I'm not sharing my whole screen. So I'm going to share my screen, and we'll just look at a sample of this algorithm in actions. It's a pretty basic algorithm. In our class on Friday, we're going to look at a whole lot more of different types of algorithm. So let me see if my screen is still shared, so I could go over to VS Code. Okay, let me get over to VS Code. Okay, so or let me just call this Euclid's. Okay, so let's call this Euclid's algorithm. Okay. If my screen is not showing up, do let me know. Okay. So let me take the question. Let me take the question from there so I can see here. Okay, here. All right. Okay, so let's go this here. All right, so okay, so all right. So we're gonna try to solve this together. Okay, I don't want to be the one solve it alone. We're gonna try to solve this together, and we have the Euclid's algorithm gives us it gives us a step. Okay, it gives us a step. I think one of the things it says is that like for two integers, okay, for two integers A and B, I think if A is greater than B, divide. Okay, yeah, if A is greater than B, divide A by B. Okay, so where A is greater than B, divide A by B, and if the remainder is 0, then you stop. Okay, so if the remainder is 0, so that should be the next step. If the remainder is 0, you should stop. Okay, if the remainder is 0, you should stop, and whatever it is, there should be B. Oh, I'll just let it be GCD. Okay, so GCD is B, and here, okay. Now, if it's not so, we're going to set the remainder, okay, to set the remainder to R. Okay, set remainder to let me see. Okay, set A. Let's set A. Set A to B. Let's set A to B, and B to R. Okay, B to R, and repeat the process again. So repeat. Okay, so repeat again. So generally, this is the idea of what Euclid's algorithm is, and you repeat the process until you have that R is 0. Okay, until you have that R is 0. So I believe you guys are with your systems. Okay, so if you are with your system, I've put together the algorithm for how it should be solved. So I like you guys to give it a try. Okay, I've put together here the algorithm. Let me make the screen larger. Okay, so I'm going to copy this text, paste it there in. I'm going to paste it there in the charts. Okay, I'm going to paste it there in the chat section so you can see it. And this is the algorithm. So you try solving it. Okay, so you try solving this, and then yeah. Okay, so you try solving this, and later on we'll come into that. So this is Euclid's algorithm, and you can try solving this. Let me go back to the class, and I'll continue teaching. So towards the end of the class, I'll take a break and see if somebody has put together the code for it. Let's continue on that sharing again. Sorry. Okay, so to give that as a practice. Right now, we don't really have the luxury of time of pausing this, so give that as a practice. So here, this is what I said we should do. Let me share the entire screen. I don't like. Okay, sorry about that. Okay, so this is what I said we should do. We're finding the greatest common denominator, or GCD, and the largest integer that divides two numbers together. So generally, how Euclid's algorithm works is that you will pick, okay, you're going to pick two integers and call one A and the other B. Now, you are doing that where A is greater than B. If where A is greater than B, what you do is you divide A by B. If the remainder is 0, then you stop and you say that your GCD is B, or you can say B is GCD, whichever one sounds clearer for you. Then here you're going to say set A to B. That's if this doesn't, let me put this otherwise, okay? So let me put this as otherwise. Otherwise, set A to B and B to R, and then repeat the process until R is 0. Okay, so this is an example of an algorithm to solve a problem. Okay, so this is an example of an algorithm to solve a problem. So towards the end of the class, I'll come over it again. If you haven't quite solved it, then I'll go ahead. But for now, let's pay attention, and I'll give you a break time where we can focus on solving that. All right, so let's continue with algorithm performance and why we need to talk about algorithms. Okay, why do we need to talk about algorithms? So here we have algorithm performance. Now, algorithm performance measures how an algorithm responds to data set size. Okay, it measures how an algorithm responds to data set size. Now, we have what we call the big O notation. But before I go into big O notation, let me try to explain what we mean by data set size. Okay, let's say, for example, we have an array. Okay, we have an array of elements, and this array of elements has maybe 4. Okay, it has 4 characters or 4 elements in it. Okay, now if you want to loop through this array and you do a for loop, for instance, and you want to loop through this array, it is going to start at the first element, then move to the next element, which is another time. So we have, let's say the time it takes to move from one element to the other is t. So starting at the first element, t, move to the next element, t, move to the third element, t, move to the fourth element, it takes a time of t. Okay, so the time it takes for it to respond to that data set, it's taken in a time of t. Okay, so that time is based on that data set. Now, if you have a larger data set, this time instead of 4, you have like 1,000 elements in this array. For example, maybe an airport having a list of, flights or passengers that have come in for the day, and you want to look through that list. That is going to take a much longer time. Okay, so there are some algorithms or algorithm types or styles or data structures, as we will see, that when the data set increases, the algorithm does not do well. So it performs poorly. However, when if the data set, okay, is small, the algorithm does very well or performs just as others. So that's what we mean by responding to the data size, the data set size. So depending on the size of the data, the algorithm may do well or not do well. So that's what we're talking about, algorithm performance. Now, generally, algorithm performance is usually measured based on worst case scenario. Okay, so it's usually measured based on worst case scenario. So if, for example, you have the worst case that it can perform is maybe if you have a large data size of 1,000 and its worst case is when it's dealing with the 1,000th element, then that will be what will be used in rating the performance of that algorithm. So algorithms generally deals with the worst case scenario, except otherwise mentioned, or in cases where certain algorithms, they rarely gets to the cases of worst case scenario, as we will see in our next class when we move into practical terms. Now, we have what we call the big O notation, okay? We have what we call the big O notation, and the big O notation classifies the performance as the input size grows or the data set size grows, okay? So input size and data set, they're basically the same. Now, it classifies the performance as the input size grows. As the input size grows, what is the difference? What is the performance? How does it perform? Now, the O, okay, the O there, it indicates the order of operation. That is the time scale to perform an operation. Now, when we talk about the time scale to perform an operation, many algorithms and data structures have more than one O. Okay, so some of them, some algorithms have more than one O because their operations might have like a nested function or operation. So for example, if you have maybe like a search algorithm, some search algorithms may need to first of all do sorting before they begin to do the searching. So in such cases, you would have the operations for the sorting, and then you will have the operation for the searching. So that's basically what it means. Okay, so we're going to talk about some of this as we go. And in certain data, searching for data or deleting data is an example. So let's look at, let me try to explain what certain data would look like. Let's say, for example, we have, okay, when we get to arrays, and I have a picture put up, I'll use that to explain. Okay, so let me just go straight to arrays. I don't want to go straight. Let me explain that when we get to arrays, I will note it down. So when we get to arrays, I'm going to use that to explain in certain data. Okay, so we have generally common types of big O terms, okay, big O notations. So the first we have is the constant time, algorithm or constant time performance of big O, and it's called the constant time. Okay, so it has a constant time or big O of 1. So wherever you hear a big O of 1, it's talking about constant time. So one of such operations is looking up a single element in an array. Okay, looking up a single element in an array is a constant time operation, and we'll see why. Another of such is the logarithmic time. Okay, so the logarithmic time, this is about finding an item in a sorted array with a binary search. And you'll see that also in our next class. We'll be looking at binary search. We'll see explanations and we'll do practical on it. Then the next we have is linear time. Now, linear time, this is searching an unsorted array for a specific value. Okay, searching an unsorted array for a specific value. And we have log-linear time, which is complex sorting algorithms with heap sort and merge sort. And then we have quadratic time. This is simple sorting algorithms such as bubble sort and selection sorts. So I just put this here. So in case you want to take your time after this class to go do your own personal research before we meet on this in our next class, you're free. So these are some big notation terms, and I'll be showing you the charts and how it performs in the next class. So let's look at data structures. What a data structure is basically a storage that is used to store and organize data. Now, it is a way of arranging data on the computer so that it can be accessed and updated efficiently. Now, depending on your requirements for a project, it is important for you to choose the right data structure for your project. For example, if you want to store data sequentially in the memory, then you go for the array structure, and you'll see why pretty soon. So we have some common data types. We have arrays, linked lists, stacks and queues, trees, and hash tables. So let's look at an array, and we'll look at this. It says here, if you want to store data sequentially in a memory, okay, memory specific now, then you go for the array data structure. And with this, I would also be explaining what a certain data is like. Now, an array is a collection of elements identified by an index or key, okay? It's a collection of elements identified by index or key, and they are a linear set of values. Now, in arrays, elements in the memory are arranged in a continuous memory form, or we call it contiguous. So let me example of that annotation. So let's look at this, for example. Okay, now we have this element here, which is 2. The 2 here has an index of 0. Okay, so when measuring or when checking index in computing terms, it always starts with 0. Okay, so it cuts across all programming languages. The index, first element has an index of 0, then 1, 2, and 3. And how the array works is this. It takes note of, for example, you want to store a variable, and this variable now is stored in a specific path in the memory, and each memory, okay, or each system memory has an address. Okay? It has an address, like a location where some information is stored. Now, what an array does basically is it takes this first index, stores it in a particular memory location, and then it takes these other ones and just puts them beside it. Okay, so it takes this one, this one will now be the key, and then just puts the other ones beside them in the memory location. So what it is doing here, it is arranging it in a continuous manner. So imagine now that you have a memory space. This is the address location, and then all the other elements are just placed alongside in the memory. So that way, when you want to access this one, once you have picked this memory location, all you need to do is just whatever it is you're doing operation, continue to the next memory location, to the next memory location, and such and such. So as a result of that, once you have gotten this first element, there is basically no more of what to do. You just have to flow through and everything. So arrays basically are very good in terms of in terms of how they are organized. Okay, so this memory location, everything is stored in a continuous memory format. So once you have this memory location, all you need to do is, if you want to access the second index, you count 1 position, 2 position, the memory 2 indexes away is what you want to retrieve. Okay, so if you know this reference position, 1, 2, 3, 4, the memory you want to receive here will be here. And as such, if you have maybe like you try to access something in the 5th index or the 5th position, since there is nothing there, it's going to return there is nothing there. Okay, so it's going to return an undefined because there is nothing in that memory location belonging to this array. So basically, that's how arrays work. Now, when I was speaking about inserting, okay, inserting data, the challenge about inserting data is, if, for example, I want to insert some data here at the beginning. Okay, I want to insert some data here at the beginning. So here, inserting the data at 2. So let's say I have some data I want to set, maybe like 6, for example. If I put 6 here, one thing that must first happen is that this 2, which was in position 0, must then be moved to position or index 1. One that is in this index 1 must be moved to this. This that was here must be moved to this. This that was here must be moved to this, and this that was here must be moved to the 5th, the 5th index, or index position 5, because they're actually like 6 indexes. So this will be like index position 5. So basically, when you are inserting something at the beginning, it's an operation that has to happen 1, 2, and everything. So it happens for all of them. So as a result of that, it's a linear operation because, as we said, talking about the n, we said the n is a linear operation. Okay, it's a linear operation, and basically, the more data sets, I should have put up the chart here. Okay, I should have put up the chart here. Let me see if I could scribble something up soon. Okay, I should have put up the chart here. I'll do that, okay, in the video. Now, the idea here is that okay, let me draw with this here. Linear operations are more of operations that increase as the data set increases, okay? So it increases linearly as the data set increases. Constant time operation is more of an operation that is constant, okay? So it's constant with the data set. Whatever time it will take it to run and irregular, it will run with the same, no matter the size of the data sets, okay? Then if then the next one we have should be more of a curve. The next one we have should be more of a curve, and we have the logarithmic time. So it first of all tries to increase, and at some point it no longer increases much. So it sort of like stabilizes. So this is more logarithmic time, and log linear time is also something similar. So I'm going to just leave this from here and use this in explaining as we go on. So in terms of linear time, okay, in terms of linear time, the larger the data set, the longer time it's going to take for the algorithm to run. So if you have an algorithm for inserting in an array, you want to insert something at the beginning, for instance, you have to push everything. Okay, so this one now, a time operation to take to put this from here. So this new index is going to become 2. This new index is going to become 2. This one will become 1. This one will become 5. This one will become 3. So basically, that time of reassignment of what is available or stored in this position is what is going to take that time. Okay, so the more information you have, the more it will be. Also, inserting or deleting in the middle. In deleting, if you were to delete this also, this one has to shift its position from being in one index to here. So this is like a reassignment of what value is in that position or in that index. So that is why we say it's a constant, it's a linear time operation. Then inserting at the end of an array is a constant time operation because regardless of the size of the array, whatever it is you are stacking to the end, you are not having to do any reassignment of what is here. So because of that, that makes it more of a constant time. So even if you have 1,000,001 operations, elements in the array, putting something at the last position is basically constant time. Okay, so you just look at it. This array has how many elements? Okay, it has 1,000. Okay, just put one at the last, and that's all. So that's that should be summarily enough. Okay, so let's look at another aspect it says here. It says here that arrays could be one dimension or even two dimension. So one dimension is this array, okay? And then two-dimensional arrays is basically when you have an array in an array. So for example, instead of me having 2 here, I could also have an array of other things. So if I have an array of other things, let's say I have here an array of other numbers or array of strings, for example, that will become an array in an array. And if I want to access them, I would have to access them using, instead of you putting just one index for the position, you're putting this one for the first array, which is this, the position in the first array. And this will now be for the position in the nested array. So that's an example of that. So you could test this out and see how this goes. So here we have linked list. So linked list is another type of data structure. And for those who deal with object-oriented programming languages, okay, if you've had some experience with object-oriented programming languages, you particularly, maybe have been familiar with the linked list in use, okay? Now, the linked list is a collection of data elements, and they're basically called nodes. Now, they contain a reference to the next node in the list. Now, what it does is it holds whatever data the application needs. So it's a collection of data elements, and it contains a reference to the next node. Now, from a memory allocation point of view, linked lists are more efficient than arrays, and unlike arrays, the size of a linked list is not predefined. So this is one thing that you'll be more familiar with if you have been dealing with a more object-oriented programming language than JavaScript. For example, C#. Okay, in JavaScript, when you declare arrays, you don't need to declare the size of the array. But in C#, when you declare an array, you have to specify if the array is going to be having 4 elements. You have to specify from the start when declaring. You are declaring the array and the number of elements that will be in it. But when we have linked list, we do not declare. Okay, we do not need to declare the size. So the linked list can grow and shrink, and the purpose of it being able to grow and shrink is because we'll see this functionality as I explain that aspect. Okay, so generally, let's take this as one element, another element, another element, another element. Now, all of these elements here, they are not stored together side by side or contiguously or continuously as we had in arrays. In arrays, all of the elements were stored in the adjacent or next memory location to each other. But in linked lists, they can be stored anywhere in the memory. However, each element, okay, contains a reference to what is the next element. So this element 38 has a reference in the node, and this reference is telling it that it's telling the system that this next element is the one following. So after this is the one following. So they can be stored in any part of the memory, but they would then have a memory, okay, a reference that shows what is the next memory location, what is the next element following. So that's what we mean by linked. So that is how they are linked together. So in arrays, they are stored side by side, but in linked lists, they can be stored anyhow in terms of location, but you then have a reference in them telling what is the next memory location for the next element in the list. Now, what is the benefit of having the linked list? One of the benefits I see in having a linked list is if you want to assign a new element, for example, you want to assign a new element, all you need to do is you grab on a new element, okay? You grab on a new element, and this new element will then be created, okay? When it is created, and you want to insert it, for example, in between 38 and 13. What will happen is you create the elements, and when you create the elements, you then tell this one, let your reference point to this, and let the reference coming from that one point to this. So let me try to draw up something so that it looks a little bit, little more clear. So let's say, for example, we have a new element. Let me draw it at the bottom here. So let's say we have a new element here, okay, that we want to add, okay, and let me call this 12. Okay, I can't draw with that shape. Let me just write 12 here. So let me call this 12, for example. Now this new element 12 that we want to add here to this list. Why is this not showing us 12? Okay, let me delete this. Okay, so just give me a second. All right, let's just leave it as worrying, okay, so it doesn't take our time. Now this element here, we want to insert this element between these two. So all we need to do is create this element, and when it's created, then you take this reference point and say, I want you to point to this, okay? Or let me clear that off. Let me undo that. I want you to point to this, okay? And I want you to point to this, okay? So this this one here goes out. Now, if you look at this, you see these other ones. So it just looks for this particular element it wants to work with, and then where are you pointing to as the next? So it takes note of where it's pointing to as the next, and what it does now is it says, okay, this two that is pointing to, take your connection from here to point to this, and then let this one now point to the one you were pointing to before, the previous reference before. So basically, that is what the linked list can do. So if you look at that now, you realize that it doesn't affect this other part, okay? So it doesn't affect this other part. So that makes it a faster operation than working with an array. When working with an array, okay. Now, when working with an array, what we saw here, let me clear this up, okay? When working with an array, what we saw here in the array is that for every insertion we had to do, okay? For every insertion we had to reassign the values. So if we want to insert something here, for example, we want to insert maybe a new element here, then we would have to move these other ones by one index each. So everything is affected from the start to the last. If we want to do that from the middle, we would also have to move each. And if we want to do that from the end, it is only then that it will be constant time. Okay, so that's the main concept about the main key difference that we could first of all note between the array and the linked list. So just by that, you see that this becomes a faster operation. So the first item here is called the head. And each of these items contains a reference to the next item, with the last one pointing to nothing. Okay, so it's pointing to null, indicating the end of the list. So where the last one points to nothing or to null, it indicates the end of the list. So that's an example of a single list. Then we also have doubly list. Okay, so a doubly linked list. So a doubly linked list has the reference point of where it is coming from. Okay, so here we have the reference point here coming from the null, indicating that this is the head. It's pointing somewhere, okay, indicating this is the next. And this one that is, here is also noting where it is receiving its reference from. So it's taking that this one here, it's going to be what it's receiving from, and then this is the next. Okay, so that's an example of a double, okay, so a double linked list. So elements are easily inserted and removed as I showed you. Now, the underlying memory does not need to be reorganized, okay? You don't need to, do like a reassignment of memory locations like we saw in the array. So it doesn't need to be reorganized. And the challenge with this is, the challenge with the linked list, however, is that it cannot do constant time random item access, okay? You cannot do constant time random item access. In an array, you can do constant time random item access because once you want to try to access something in this location, here, once you want to access something in this location, you have your index and it knows the position, and then all you just need to do is to count to that position and access it and say, okay, so if you, for example, you want to access index 4, it will just do its count to index 4 for you to know that, okay, this is its position. But in a linked list, if you want to access this here, for instance, it needs to, first of all, know what is the head and then how it's linked to get to this point. So in that regard, random access is not easy for it, but once it has the memory location as the head and everything, it flows through. Then item lookup is linear in time complexity, which means that it's more of an expensive operation. It's linear in time complexity. So item lookup is basically a constant time random item access, which that's just an example of what that would be. Okay, so we want to look at stacks. When I talked about in our first class, talking about the event loop of Node.js, okay, talking about the event loop of Node.js. Okay, now talking about the event loop of Node.js, I took time to talk about two concepts, a stack and a queue. We said we have the event queue, okay? We have the event queue, and then that is where all the requests are placed. And then we have the stack, and the stack or the pool was where we had operations that were expensive operations were sent to by the event loop. So it was there in the pool and it was being worked on. So what we had in the pool was a stack, while what we had in the event queue, as the name sounds, was a queue. So let's look at what queues are and understand them in basic. Okay, so let's start with a stack. Now, stacks are collections that support push and pop operation. So the last item, push, is the first item popped. The last item added is the first item removed. So stacks are basically last in, first out data structures. Okay, so last in, first out data structures. So as we see here, we see 3 here is being put last. And if you notice, you see here, I put this here to like symbolize that you cannot, this one at the bottom cannot be accessed first. There's no like point or way of accessing what's at the bottom first. So it has to be unloaded. Okay, so it has to be unloaded. So like you see here, popping before you can access what is placed first. So what is last in is going to be the first out. And conversely, what is first in is also going to be the last out. So that's a stack operation. Okay, so putting an item in the stack operation, let me go over this again. So put an item to a stack is a constant time operation, since it doesn't matter how many items are already on the stack. So if you want to place an item on the stack, it's just like you placing something at the end of an array. It doesn't matter how many items are already in the array. At the end of the array, it's a constant time. All you just need to do is you are placing something. So even if there are a million items, all you just need to do is place an item there at the end. So it's a constant time operation, since it doesn't matter how many items are already on the stack. And popping an item is also a constant time operation. So let's look at the difference between a stack and a queue. Now, a queue, as you know, in your own common experience with English, is first come, first serve. If you have a queue and people are not breaking lines, and there's no favoritism, there's no nepotism and all that, then you would have it as a first come, first serve basis. So here you can see it, this looks more like a tunnel, or more like a tunnel, and what comes in first will be the first to be removed. What comes in first will be the first to go out, and what comes in last will obviously be the last to come out. So if you look at it now, conversely, to the stack operations, what goes in first in the queue operation is what comes out first. So queues are basically similar in the sense that it supports adding and removing items with ease. However, it's a first in, first out data structure, and they are also constant time operations, because it doesn't matter, okay? It doesn't matter what the size of it is. Getting something out of it, you can access what is at the end. Now, in this case, you cannot access the first element here until you have taken all of this out. So if you want to pop everything, you can't get to one until you pop everything out. And the same way it goes also for this. If you want to access the last, you have to pop or remove everything from the queue until you get to the last item. So let's consider some of the practical items of a stack. Now, a practical item of a stack could be when parsing, when we use to parse and evaluate various forms of expression statements. Let me try to use a code explanation to this, because it's looking vague. It's looking vague. So let me try to give you an instance of what this would be like. Okay, so we still have this here coming or waiting for you guys. So let's see. Let me look for a simplistic example. Let's say we have, for example, a variable here. Let me just call it a variable. Okay, so let me just call this let. Okay, so let's say we have a string. Okay, let's say we have a string is equals to okay. Let's say let me call this string A. So let's say we have string A is equals to A. Okay, and string B. Okay, so let me say string B is equals to B, and let's make this B. Okay, and let's say we want to have string C. Okay, so let's string C. So now I want to use an example now. So let's say we have string A, okay, plus string B, string B here. Now this is one operation here, okay? This is one operation. And let's say I want to do something to it, like let's say to lowercase. as a function now. Okay, this is a stack. It is going to, first of all, try to do this first. And then from here, after it's done this, then it will move into this. If we had something else to do, so maybe, for example, I want to maybe parse this. Okay, so maybe I want to parse this. Okay, so maybe I want to parse this to maybe lowercase. Let me just do this to lowercase for instance. Okay, okay, I've done lowercase. Let's say it's uppercase now, just to have more operations here. So it's going to start by this first, doing this operation. After it's done this operation, the value that is returned is going to then move to this, okay? And after this is done, then it's going to move to this. So this is just like a rough, sketchy way of me just trying to explain, you know, what was said there, because it was looking at verbose. Okay, so it's looking at verbose and, you know, so let me get this. Oh. All right. Okay, so it's often used to parse and evaluate various forms of expressions. So when you have expressions, you want to first of all take the last you know, set of things that you want to do, then from there move to the next, and from there move to the next, and then you have this. And then here we have another example is backtracking, and this is in your browser back tab. So if you want to go to backtracking, maybe like you want to check your history and you click back, it's looking for the last, you know, the last element that was added. So remember, it is a last in, first out. So starts at last in, first out. So it's looking, so backtracking is you're looking for the last thing that came, okay, the last thing that was added, last in, first out, last thing that was added, that's the first you can access. So when we are saying first out, think of it as the out is accessing. So last in, first out. The first, what you can access first is the last operation or the last element that was added. So that's backtracking. Then for queues are applicable for order processing. So when you have order processing, you want the order to be processed in the manner in which they came, taking first come, first serve basis. That's order processing. Another example is messaging, okay? Another example is messaging. So if you're having messaging now, for example, you're dealing with WhatsApp messages, you send messages, the messages will be recorded, and based on the nature of the messages you send, it's possible that some messages, you know, might not be time. However, they will be tracked. This was the last that came in, you know, so it should be the last to deliver, while the first that came in should be the first to go. So this was the first message you sent. This should be the first message that, you know, goes in. So imagine now that you're sending multiple messages over, you know, WhatsApp and HTTP module, and the message is going in and it's not coming in the order in which you sent it. So that will not be a correct implementation. So there you want to use a queue. First in, first out. This was what was sent first, then it should be what you deliver first. Okay, so that's an example of a queue in practical terms. All right. Before we go into trees, okay, I want to take a pause and you know, hear from us if there's any aspect, okay, there's any aspect that is unclear thus far in the class. So at this point, I would like to take feedback. Is there any aspect that you want me to touch on again or explain, or something you didn't get clearly? You can put your hands up, okay? So you can put your hands up so I can call you. Anybody? Okay, so if we're good to go, yeah, just drop a thumbs up. Okay, so I know we're good to go. If you're good to go from your side, I just drop a thumbs up so I know you can hear me and we're good to go. All right, I'm waiting. Any question? Okay. All right, good to go from that side. All right, great. All right, great. Okay, so great. All right. So the next we want to look at is called trees. Okay. Next one to look at is called trees, and all we've been looking at thus far are more of linear algorithms. Okay, or sorry, linear data structures. What we're looking at thus far have been linear data structures, and we want to look into a lot more different type of data structure, which is trees. So a tree is a non-linear hierarchical data structure that consists of nodes connected by edges. So this here are the nodes, and they are connected by edges. So this is an edge, okay? So this is an edge. This is another edge, an edge here, an edge here, edge here. So they consist of nodes, okay, connected by edges. However, in a tree data structure, there can be one edge between, okay, there can only be one edge between two vertices. So a node is also like a vertex, okay? A node is also a vertex. Now, a node is also a vertex, like a point. The word vertex and point and nodes, they are, one and the same. So a node is a vertex. Okay, so there can only be one edge between, the edges. There is a more complex non-linear hierarchical data structure also, rather not really hierarchical, but somewhat similar, and that's called graph. And then when we get to GraphQL, which is towards the end of this program, you get to see it in detail. There you can have like multiple. Okay, you can have multiple edges connecting, two nodes. So here you can have multiple connection, but when we're talking about trees, there can only be one edge for every two nodes. So this is one node, one edge, one node, one edge between them, one edge between them, one edge between them. So that's how it is. So you don't have something going from here to here. You don't have this going from here to here. There's no link. So that's a tree structure. Now, what is it about trees? Okay, what is about trees? Why was there a need for tree structures? Now, different tree structures allow quicker and easier access to the data as it is non-linear, okay? And it is a non-linear data structure. Now, another example of a tree structure that you probably use every day is your files directory or file system. Okay, now in your file system, you have directories, you have folders, you have files. So if you are trying to access, for example, a file, all the different paths that you take to get there will be your nodes. So the different specific folders will be the nodes until you get to the file, and then the connection between them will be the edges. Okay, so a node basically is an entity that contains a key and value. Okay, it contains a key or value and pointers to its child nodes. The last node of each path, they are called leaf nodes or external nodes. So these external nodes or leaf nodes do not contain a link or pointer to child nodes. So for example, if this here is a child node, sorry, a leaf node, it's also a child node because it's a child of this node. So node 1 here is a parent node to node 2 and to node 3. Node 1 here is a parent node to node 2 and 3, while node 3 is a child node to node 1. Node 2 is also a child node to node 1. However, it's also a parent node to node 4 and to node 5. Now, node 3 here doesn't have a link or pointer to any other child node. So in other words, it is a leaf node. Node 5 is also a leaf node. 8, 7, and 6, or 6, 7, and 8 are also leaf nodes. So 1, 2, 3, 4, 5, 6, 5 rather. Oh, 1, 2, 3, 4, 5 are all leaf nodes. Okay. So the node having at least a child node is called an internal node. Okay, so the node having at least a child node is called an internal node. So here we have this here is having at least one. This is also having at least one. So you can call it an internal node, and this is the parent node. Then the edges is basically just a link between any two nodes as I've explained. So this is a tree structure, and you can have this in your file system. So it's a way of you being able to access things in your file system. Another thing I would consider as a tree structure, not necessarily that it is, okay, because it has so much in it, but the way we have objects nested in objects, that's another example, because you can look at that as a tree structure. If you want to access an object in an object in another object, that's a tree structure. But there you have a combination of yes, the tree structure. Then you have you can have an array in an object, so it makes it more or less like hybrid. Okay, so it makes it more or less like a hybrid. But yes, you consider it in some way as a tree structure. But a very good example is your file system of your directories or folders. Now, one last function or one last structure we'll be looking at today is called the hash table. Okay, it's called the hash table. Now, what is a hash table? The hash table is a form of associative array structure that maps keys to their associative values using a hash function. So here you have function here. Okay, so you have here a key. Okay, this is key one. You have here a key, which is key one, and it is mapped here using a hash function to the value. All right, and then you have key two mapped to key one, and what you have here is the hash function. So the hash function is more of like a key to value mapping, and all of this, they are unique. Now, when we get to, I think it's should be the 6th or 7th week, where we'll be looking into authentication. We'll be looking at hashing, cryptography, where we'll be working with Backtracking to hash our passwords, to hash functions like OTPs, and then to store them in a database. So this is one of such functionalities that comes into play there. But this is basically just an explanation in the basic term of what the hash function is, or hash table is. So it's basically a form of associative array that maps keys to their associative values using a hash function. All right, so that brings us to the end of the theoretical part of today. Okay, so we're moving into I would take questions while we look into the algorithm that I've given. So I've given us the algorithm, and I would like us to work on the algorithm. So I'm going to give roughly about 2 minutes or 3. Okay, you can try working on the algorithm now. Solve it. So I try working on the algorithm. I'll take questions if there are questions. Okay, so I'll take questions if there are questions. So this is the algorithm is put up here. I'll start working on it. Okay, so this algorithm here is put up here. Start working on it, and in roughly about 2 minutes, since I can't pause, I can't quite pause the recording. Okay, so your time starts counting now. So let me set my timer. All right. So in 2 minutes, I'm going to solve this. So if you want to quickly solve this, yes, you go ahead. So this algorithm, so let's go over the question here again. This is a Euclid's algorithm, and it says here we should find the greatest common denominator, GCD, of 2 integers. That is the largest integer that divides 2 numbers without leaving a remainder. And here, this is the algorithm. Okay, this is Euclid's algorithm. So while you can think of a way of solving it using functions like, you want to use math.floor, or to know which one is the least or which one is the greater, and everything, you might want to try doing some other way of doing comparison, like using the greater than or less than sign. whichever you want to do. Okay, so just go ahead and do that, and then once you've done that, you can post your code solutions. Okay, so you can post your code solutions in the group. Okay, so I'll take fastest response. I'll take fastest to response. So I've already dropped the question there in the group. The question there in the group is pretty much still the same. So, all right. So, any question for me? Thoughts 5. Your question is from today or from previous classes we've had. You can raise your hand. Okay, I have one here. This is from Uzo Machuku. So, I have one here, and yes, he even has a console. Okay. Okay. All right. So let's take this here. Let me create a new. Folder for that. Okay, so let me create a new folder for that. Let me just call this index.js. Okay, index.js. So let's get this running. Okay, so this is from him. Yes. Okay, so this is taking in 2 functions A and B. Yes, it's calling this one large, and then it's calling this one small. And how it's checking if it's large is if A is greater than or equals to B. Okay, then he's asking. So this is the conditional statement. Okay, great. I like this. So this is a ternary operator. So it's checking if this is true, then it's A. If it is false, then it is B. Okay, then here you have small is equal to Okay, so here you're doing our ternary operator. Is B. I like this yourself. This is interesting. So here what you're doing here is you're asking if large is equals to A, okay, and then if it's not equal to A, what's going on here? You're asking if this large is equals to A. Question. Well, let's run this. Let's run this. Let's see. Let's run this and let's see. So here we're going to run this and index here. So let's see our results. So here we have 0. We have 0, so it means that something is wrong in your code. You are returning 0 instead of returning the factor. Okay, so this didn't quite work for you. Okay, so here we tested with 36 and 42. So this didn't quite work. Let's go. So let's see another person in the chat section. Any other person in the chat section? Okay, so Machuku, you might want to check it out again. If we were to debug your code, let's see what we have here. We have large is equal to. Let me start by console debugging. Okay, so let me consider what you have as large here. Okay, so let me see what you have as large. Node 1 index, and then okay, so here you have large. Okay, great, and let's see what you have as small. Okay, you have large as 47, you have small as 47. Yeah, this goes. So where exactly are you making your error? Okay, so if large,
Ben.
Yeah,
try passing 20 and 8 to it.
Okay, 20 and 8 to it. All right. Okay, do we have any new solutions? 20 and 8. Okay, so 20 and 8 is given 4. 20 and 8 is given 4, but when you use 36 and 47, it's given 0. Okay, because there's no there's nothing common between the two of them. All right, great. I think that should be why. Let me use 42 here. So let's see. Let's see 42. My screen hanging. Okay, so 42. Yeah, you have 6. Okay, great. 42, 6. All right, let's see. So let's try one more. So let's try one more. What if we have a negative? What if we have a negative? What do we have? We have 0. Okay, so negative. That's great. Okay, all right, that's great. That works. Okay, that works. Okay, so that's great. So that gives us a good solution for that. Yeah, so well done. Okay, so well done. what's the name now? Well done. So that's right. So this works pretty fine. And for just one more data set, let's have 102. Okay, so let's have 102. Okay, with 10 and 8. With 10 and 8, why is there no? Let me check if this is right. With 10 and 8. Okay, so with 10, I am not seeing with 10, 6, 4, 0. So with 10, at least there should be a 2 between them. Let me try with 5 and see. With 5, you have 5, yes. With 2, you have 2. With 8, why do you have 0? So something is wrong here. Okay, something is wrong here in this place, and something is wrong here in this place. So you might want to check what exactly is wrong. Okay, I want to check what exactly is wrong. So generally, when testing algorithms, in what you have is you'll be given like various different data sets. So like here now, it worked perfectly with this, but now using 10 and 8, it's not working. Okay, then so when working in testing, you'll be given like lots of different data sets to test your algorithm with, and when it is tested, in some cases it may fail, in some other cases it may pass. Okay, so that should also be an approach you want to consider. You want to test your algorithms in different ways. You want to ask yourself, what if I have 8 here and I have 10 here? Okay, so what if I have 8 here and I have 10 here? You see here it's still giving me 0, and this greatest common denominator here should be 2. So you want to look into this. Okay, so you want to look into this, check exactly what's going on wrong here. Okay, so let me just give by way a solution of how we do this. Let me just give by way a solution of how we do this. Something like I said, algorithms are basically just your own step or your own approach to how you solve a challenge. So it is not necessarily that this is the best. You may see like a cleaner code, something very clean, something very straightforward. I've done some algorithm tests and I've gotten like 100% in some. And then when I saw what others did, I was just like, I prefer theirs. Okay, I prefer theirs to mine because in the context of what they did, theirs was more like a one-line code, so it didn't stress me. It was more like a one-line code, and it provided the solutions. So here I want to use a while. Okay, so I want to use a while operator. I think the challenge you might have had is maybe using a for or something, but I want to use a while operator. So while b is not yet equals to 0, we'll be looking at this when we look at recursion in our next class. Okay, our Friday class, we're going to look at recursion, and we will see the benefits of using the while operator. So while b is not equal to 0, what I want to do is I want to say let t, okay, so which should just be like a temporary self. So let t be equals to a, and then a should then be equals to b. So what I'm doing now is I'm reassigning value. Okay, so I'm reassigning value, like taking a new value for that, and then let me do this and I'll explain my own approach. Okay, so I'll explain my own approach. So what I want to do here is this. Okay, so this is basically what I want to do here. I'm saying while b is not here equals to 0, which is here. It says if the remainder is 0, then stop. Okay, if the remainder is 0, then stop. Then otherwise set a to b. This is what I've done here, and set b to okay, I called it t. Okay, so let me just call it r. So it's the same you see here when you read the code. So let me set this to r. Okay, so set b to r, and then repeat the process until r is 0. So I am checking now if B, okay, is equals to R, what you call it, if B is equals to R, then divided by 0. So this is modulo, okay, so modulo, so that's what I'm doing there. And then here, when it finally breaks, or when it finally comes out, I want to return A, which is, the value. So I hope this runs. I hope this runs. So let me give it a shot, okay? I hope this runs. But if it doesn't run, we just debug it and check what would be the solution. So, okay, so let's say GCV or GCV, that's what I called it. What are the values we had here? We had, okay, 36 and 42. Okay, so 36, 42, 36, 42. Okay. And please, it's not like I'm doing a correction. I'm just showing you an example of like how it could work, because this is not a correction. You might come up with even like one line of code that does it perfectly. Okay, so in algorithm, there is no yet, there are some algorithms that solve a process better. They are tested and trusted over time. And those algorithms are what make a name. Those are the ones that we then get a name for. So you're going to hear Euclid's algorithm, you're going to hear bubble sort, you're going to hear. So those algorithms that over time have been tested and they have been able to prove, their ability in solving a particular type of challenge or problem. Those are algorithms that are accepted. Okay, so generally, okay, so let me do more just in case I have issues I want to resolve. Okay, so all right. Okay, so here, okay, so this works perfectly. So here I have between 36 and 42. This is 6 times 6 and 6 times 7. So the lowest is 6. This is 4 times 5 and 4 times 2. So the lowest, the greatest common rather is 4. And then this is 2 times 4 and 2 times 5. And greatest common is 2. So this is like a way I would solve it based on the way it was described here. Okay, so based on the way it's described here as the algorithm, this is that solution for that. So generally, the purpose of testing, okay, algorithms, the purpose of testing algorithms is because there are like some operations that are expensive. So let me just do something in the new index. Okay, so let me just do something here in the new index. So there are some operations that are expensive, and I want to use that in closing. So let's say, for example, you have a for loop. Okay, let's say, for example, you have a for loop. A for loop is okay. Let's say for let I think I missed the I the last class. So let I equals to 0, then while I is less than let's say 5 for a start. While I is less than 5 for a start. I plus plus. Okay, so I plus plus, and okay, so for this I want it to do something. So let's say console.log or something. Let me say console.log A, for example. Now this operation here is going to run for every single time. It's going to run 5 times. This loop is going to repeat itself 5 times because there are 5 things that it wants to do. So let's say this is an operation now. Each time it's going to loop through this is one of those times. So when we were talking about the linear time, this time that it takes to loop through this once will be constant time. But having it to come over again, the second time, the third time, and the fourth time is then going to be, based on the number of times it has to iterate. So if the number of times it has to iterate is, let's say, n, okay, so let n be equals to, let's say, for instance, the 5, the number of times it has to iterate. And this here is n now, saying 5, okay? Now, it is going to go through this loop n number of times, okay? So it's going to go through this loop n number of times. As such, that is why we say it is, where's the O? Okay, so this is, it has a big O of n, okay? So it has a big O of n, and as such, this is a linear time operation because it has a big O of n. But for an operation now that runs through once, okay, an operation that runs through once, which could be, let's say, let me say, for example, let's pick an array. Let's say we have an array that has, let me not make it a constant. Let's say we have an array that has fruits, for example, and these fruits, we have an array of, let's say apple. Okay, so apple, cherry, let's see, we have strawberry. Okay, strawberry. Now, this operation now, getting one element here, okay, getting an element here, for example, fruits in this index here, the index of, let's say 1. This is going to run through once and fetch, so this is going to run through once and fetch what is here, which is cherry. So it is running through once, fetching cherry and returning cherry here. So this is running one time, and as such now, this is more of a linear operation. So I'm trying to like bring it home in practical terms now, okay? So this here now, which is just this now, is more of a linear operation, okay? So this is more of a linear operation running through here. But when we have to now insert something, now, you know, inserting is not the same thing as, if I was to say, for example, fruit is equals to maybe mango, okay? Fruit at this position equals to mango. This is not an inserting, this is not inserting, this is basically just replacing. So it's going to pick this, the memory location, and replace this. So that would be a constant time operation. But when we want to insert, we want to insert something here at this point, and then we assign this one, this new value, this one here will take a new memory location adjacent to it. So I just want to make sure that we are clear on that aspect. But if I was just accessing, okay, if I was just accessing or even accessing just for the purpose of reassigning that variable, it's a constant time operation. So this here would be a constant time operation because you don't have to like loop over or go over a certain number of times or go over the iteration. So this would be having a big O of 1. Then when you have something like, let's say a for loop, for example, okay, and then you now have in the for loop, you now have another for loop, and then how did I get wrong? Okay, so okay, I didn't copy that. So let's say you have another for loop here, and then maybe this one is for j. Okay, so this one is for j, and j is equals to, let's say n also. So they have the same thing here. Okay, and j here is less than yj is less than n j plus plus. What is going to happen is this is going to run the first instance, picking the first time or the first position. It is then going to access this for loop. This for loop will run the first time, second time, third time. So remember that here we have operation 5. Okay, it's going to run first time, second time, third time, fourth time, fifth time, and then it is going to release and then come back to this one. This one will run again the second time. Okay, 5 again, then third time, 5 again, fourth time, 5 again, fifth time, and then you then realize that this is happening 5 times, which is basically an n times n time, which is an n square operation. Okay, so as such, Operations like nested for loops are operations that you want to mostly avoid in any algorithm, because when you have a large data set of, let's say, like 1,000, imagine now that this loop has to run like 1,000 times. You can imagine how much time that would be. So a loop that has this kind of structure is more of a quadratic, okay? So it has more of a quadratic time, and it's very expensive. Okay, so it's very expensive. You want to avoid this at all possible costs, unless you cannot avoid it. So one of such examples of an algorithm would be the brute force algorithm. You should have heard of brute force. Okay, should have heard of brute force. So let me give an example of brute force. We'll look into algorithm examples in our next class, and I will show you more examples. But let me just give an example of brute force. Let's say, for example, you have a padlock, like the conventional padlock that had 3 digits, and each digit is from 0 to 9. So you first start by picking the first element and combination 001 or 000. Does it work? No. 001, no. 002, 003, and 009. Then you now have 010. So you notice that for this operation, it has to go through all the list of possible occurrences before the chances of getting to that combination. So this is an example of such, and it is very expensive. And that's one of the bases for which we are asked to, when we want to create our passwords, we say the password should be anything from 8 characters above, or depending on the kind of site. We say, okay, we don't want to use only 8 characters. We want the password, because 0 to 9 is just only 10 digits or 10 possibilities. And when you multiply 9 times 9, okay, or you multiply the 0 to 9, that gives you 9 possibilities. Then you have more of like, let's say 9 factorial, then the number of combinations 3, and the number of possible combinations 3 times 9 factorial. Right now, I can't do the maths, but you have it for, let's say we have only 1 digit now. You have 10 possible outcomes. If you then have 2 digits, you have 100 possible outcomes. Okay, you have 100 possible outcomes for 10 digits. And then if you have 0, you have 1,000 possible outcomes. And then when you have it in 8 places, this is the possible outcomes. However, when you add characters now, like A to Z is 26 characters. Okay, so A to Z is 26 characters. And when you add 26 characters plus the 10 possible characters here, it makes it a larger list. So for 26 plus another 10, which is 36 possible characters. When you add capitalization now, so it could be capital letter or small letter, you now have a new set of characters. So you have, let me just write this out. You have 26. Let me start with 10. Okay, plus 26. Then plus another 26 now in capital letter. Then plus the number of special characters you have. So let's see. With that now, that gives us 36, 56, 56, 66, 66 plus 6, 72, 72 plus that, that's 78. So that gives us 78 possible characters. And with this here now imagine 78 times 8 times 78 times 8 now. And then that is just about for 1 character set if you have 2. Okay, you have 2 now, as opposed to you having 10 here. Okay, as opposed to you having 10 possible characters, and then when you have 2 digits, you now have 100 possible characters. For 2 digits, you're going to have 78 times 78 possible characters. Then for 3 digits here, where you have like 1,000, you would now be having 78 times 78 times 78 possible characters. So that makes brute force very difficult, but you have powerful machines and computers that can run this in milliseconds. So then they say, okay, make the characters, make the, what you call it, make the number of characters that you use in your password so large so that you could then have this amount of time that it will take for it to load. So now imagine that when you're dealing on maybe things like cryptocurrency, they ask you to use like 16-digit characters. That's because they know they are even now more powerful machines or computers, and they want it to be that brute force will not be able to deal with memory space allocation and all the time complexity that it needs to deal with that. So that is thinking in terms of algorithms can be expounded by you understanding, how algorithm works, and your code could run faster. You're also the way you plan, the way you plan and deal with things in terms of data security and cybersecurity issues could also be modified. So I think that would be that for today, and I'll take questions if there are any questions for today. So that will bring us to the end of today's class. If there are questions, put up your hands so that I could take questions. Yes, please. If there are questions, do let me know so I can take questions. Okay. I have Moyo. Moyo raised hand. Please ask a question.
Okay. So, good evening.
Yeah. Good evening. Could you speak up, please, so I can hear you better?
Okay. Yeah. Sorry. Good evening. Okay. So question is first, what's the application of the brute force? The brute force that you just explained. Then sorry, I would also want you to the solution to the is it greatest common factor that you explained.
Yes,
Sorry,
yes.
can you please recap, break the logic down? The code was too quick, so I didn't really know how it went. That module, I didn't know how it do stuff, and made it look seamless. So can you just help me break the
Okay. All right. So talking about brute force, like I said, the purpose of brute force most times is they are used for crackers, okay, for people who are trying to break into a security system. So in one case or one use, it could be more for the government or against, okay, it could be more of trying to break into a site. So if you watch most of all these movies where you see them, maybe they go to a door that has more of a computer lock, and they just plug in a device, and then you see the device running fast and runs a multiple simulation, and after like a few seconds, you see the door is unlocked. That's brute force at work. Okay, so that's brute force at work. So it's running through multiple possible codes within a short time to see which one will be the right fit. So if your password, for instance, is 123, then it's earlier, and it will quickly assess. And if it's maybe 999 or something, it might be late. Depends on the algorithm that they have. Okay, you might set up a different type of algorithm. So depends on that. But brute force generally is more of repetitive, depending. So if you have like 3 positions now, you can imagine now you have a for loop for all the different indexes that you have. So this one here is dealing with 2 indexes, and it's going to take a long time. So going over the Euclid's algorithm, let me just quickly go over that. If any other person has a question, you could also put up your hand so I could bear that in mind while trying to answer this. So let me start first of all by doing a console log for clarity purpose, so that we see. Let's say console log. Okay, so let's say console log of okay, so let's say console log of 36. Okay, let's say console log of let me do 20 modulo 4. Okay, 20 modulo 4. And I want to show the answer I'm getting here is 20 modulo 4. So node none. Okay. Node none Euclids. Okay. Let me comment all of this stuff. Okay. All right. So 20 modulo 4. That isn't what I'm looking for. Okay. 20 modulo 4 is 0. Okay. So 20 modulo 4 is basically returning the remainder. Okay. So returning the remainder. And here we have, let me use 5, it's giving 0. Let me use 6. And if I use 6, you see it gives a remainder of 2. Okay, so it gives a remainder of 2. So what I'm doing here is saying, I pick in here, let's say we have 36 and 42. Now, I am saying while B, which is this point here where I'm checking. So this is this point here where I'm using this modulo to check if B is equal to 0. Now, while B is not equal to 0, stay in this loop. So while B is not equal to 0, stay in this loop. Now, at the beginning, I'm picking this first parameter from here, and I'm saying let R, okay, let R be equals to the first one, okay, and let A now be equals to the second one. So I'm just doing a reassignment. So let R be equals to the first one, let A be equals to the second one. Then now I am checking now if B, now this B here, remember that this R that I've taken here is what is representing the value of A. So let's say, for example, we have here, this is 36 now. Let me plug in values. So look here, this is 36. And let's say this is B now, which we've gotten as the second one, and B is 42. The first time it runs, okay, the first time it runs, since 32 is smaller than B, this is what's going to happen. So 32, sorry, 36. 36 here is smaller than B, which is 42. You see here now that it is going to be 0 remainder 36, and then they will now be reassigned. So that by that way, what is going to happen now is the next time it is reassigning, it is now exchanging positions now. So here, when it is coming in, we've already taken that this is B here, and then here we're now saying arrow now is going to be taking A. So it's more like a reassignment now. So it's more like a reassignment of what was there before to switch the positions, just in case one is bigger than the other. So when it flips now, we then have 42 and 36, and then when we have 42 and 36 coming in the next time now, okay, 36 now, we then have that, sorry, please. Oh, okay, I was supposed to do that elsewhere. Yeah, I was supposed to do that here. Okay, so here we have 42 and 36. So as this is coming in the next time now, I have 6. 6 is not equal to 0, okay? So it keep on reassigning over and over again until finally I then have that what is coming in is the least number that can be divided, okay, the least number that can be divided. So it's like repeating the process over and over again until I get that value. So it's just a switch of positions. I don't know if that was clear to you. Did you get that? Who asked the question? Could you answer? Let me put this here. Okay, let me put this here. So I'm going to console.log R minus B. So I'm going to console.log this for you, so that as this runs, you will see you will see the operation. So let me do it this way. Okay, let me do it this way. R, let me use string letters. Okay, so say R. Okay, so R is equals to R is equals to R. Okay, R is equals to R here. Then comma B. Okay, B is equals to let me do this again. B is equals to B, and then let me copy this. Okay, so I'm going to put this here like this here, and then I'm going to do this like this. Okay, so I'm going to say this is equal to, sorry, this is equal to this. Okay, then let me close this from literals. Okay, so I want to do like so that you see the values at 8 points in time. So let me close this up and do this. So what I'll just do is I'll use Node to run this. So let me use Node to run this. Okay, so Node E. And I have what is happening. Let me do this one. Let me do this one. Oh, I haven't given a value, sorry. Okay, so so if you look at it this way now, so you see at this point here, coming in, the first value is 36. So here is 36. The other value B is 42. And then here now, we're now saying the value R, the remainder we get now, 36 divided by 42, 0 remainder 36. Then the next time it runs, you see it's replaced. So we have 42 here. So it's replaced R. So R now is taking in the value of A. Okay, so because what we have done here now is we've said A is equals to B. So this is where the switch is happening. A is equals to B and R is equals to A. So the A here before, which was 36, now will now become B. Then A will be reassigned the value of what was B before. So that's which is taking place here. So we see that here, 42, 36. And when we do that division, we see the remainder is 6. So it's not yet equal to 0. We'll do that again. As we're doing that again now, okay, so here, what do we have as B? Our B here is 36, and that becomes a new A. Okay, and what we had there as the R will become the new B, which is R. So R becomes the new B, which is 6. And then 36 divided by 6, we have 6 remainder 0. So the 0 is here. So at this point, we break out of this, and then we can then return A, which is currently holding the value. Okay, so that's that's how it works. So I will leave this consider log here so you can look through it and everything. The first time I learned the Euclid's algorithm, I'm telling you, it took time for me to understand the process, but I then have to realize, yes, there was a switch. So B becomes R, or basically A. So B becomes R, this becomes this becomes that, and that switch is moving on. So that was when I then understood the concept. So it'll take time to internalize it. Yes. All right, great. All right, so great. All right, so that would be much of what we can do for today. Let's prepare ourselves. I'll just give you a heads up. What we're going to look at in our next class is something I would like you to actually go and practice. Okay, go and learn ahead, practice, so that when we come to the class, I will give you the algorithm to give it a shot. Okay, so I'll give you the algorithms to give you a shot, and I would like to see your responses. So I'm going to mention them. I'm going to be looking at recursion next class. I'm going to be looking at sorting data using bubble sorts, merge sorts, and we'll also look at. I think we should look at those two. Okay, I think we should look at those two for a start. Those are simple concepts you can easily see online to learn. So that's the heads up. I'll see you guys in the next class. Thank you so much for listening, for watching, and then being here. Let's be here 3 minutes before our next class so we can start promptly. So for closing remarks, I want to hand over to Prosper to give us some closing remarks. So Prosper, could you give your closing remarks? Thanks.
Yeah, guys, wonderful time again, right? So just prepare for the next class, right? Go over a few algorithms, and yeah. So you see from this one we implemented, the other guy's solution was not exactly wrong, but was not for some use case. It became the data that was passed to it now showed another output, right? So these are some kind of things you would want to consider when doing your algorithms, because the data sets are going to be different at each different time. So some algorithm might break during if the data sets become too large, and in some specific cases, just like we saw. So yeah, so these are kind of things we would want to consider while writing algorithm. So prepare for the next class and all. Thanks for your time.
I think your line is breaking up, Prosper. The line is breaking up. I hope you've heard the much of what you were saying. So I don't know. Are you back? Is your network okay now?
So you guys can hear me?
We could hear you, but it was breaking up.
Oh, okay. I'm stopping in a noisy place, right? So let's just take it from there.
Okay, now, so thanks everyone. I'll see you guys in the next class. I'm going to be dropping on Slack tomorrow what we'll be looking at on Friday, so that you can have ample time to read ahead. And I'm not saying you should go and read ahead to start flooding me with questions. No, I'm saying you should read ahead so that you can assist in some of the exercises. Okay, we'll have exercises that we could do live, and it will be great to have you guys do them. So that's the purpose of reading ahead. So don't come after me with questions, unnecessary questions anyway. But I'm always happy to answer your questions. So I'll see you guys in our next class. Have a very wonderful evening. Good night, everyone. Free